Good morning, everyone. We're going to do another demo project to showcase some interesting ideas and possibilities in relation to ignition and deep learning. So this project is going to have a handful of different levels to it as to how we get to the end potential outcomes of it. So initially we're going to talk about this page, which is all the data pre-processing and model training towards the bottom, and then we're going to talk about the ignition system design, which is over here. And then we are also going to talk about the Flask server, which is this one. And then we are also going to briefly discuss the persistent checker for this system. So have multiple options of how these things will work and go together. So originally, this data set is off of Kaggle. So the oil well CSV is just a sample piece of data that you can get access to online. But all I did was I took that data and we did the pre-processing that's required to actually use the data effectively. So drop the columns that I don't need, mostly this one, because I don't really care about the date or time. That doesn't really matter too much to me for what I'm trying to do. The columns, and then we just rename them so they're actually meaningful and not unnamed. And then we just got rid of the first top two rows because their repeats are empty, right? So get rid of all those. And then usually there's a little bit more cleaning that goes on with this system just in general, because sometimes you'll have to go in and deal with missing values or null values or whichever. But luckily this data set was fully complete, so I didn't have to. But generally the process for that is if it's categorical, you take the mode, in other words, the one that's most repetitive, or if it is numerical, you take the mean or the average of the entire data set and you fill those null values in. Luckily, didn't have to do that, but it's not a big deal either way. And then this was the output for all of these different things. These are just unique values. And then we come down here to the correlation matrix of a seaborne heat map. So basically all this is it is mapping the correlative value between each feature. So for example, volume of liquid, cubic meters per day, and reservoir pressure at any given moment has a correlative relation of 0.89. So that, for example, could have been potentially removed because it's just so relative to one another that you could get similar data without it. But because there's only 7 features in the entire system, I wasn't too worried about keeping it, so we just left it. But usually you'd leave that up to a domain expert. You'd ask them, does this matter enough, or is this so incredibly vital that I have to have it, kind of thing. But seeing as how it's just me, I decided just to keep it because it was a small enough piece of data. But then we come into the more interesting part of this. So this top part was mostly just cleaning. This is set up for model training. So we split our features into independent and dependent features. Basically, these are the relative features of interest that we're going to be predicting off of, and then this is the prediction value. And so obviously, because this data set didn't have anything else really going on with it other than how much am I getting in terms of oil in this instance, I could have also predicted for volume of liquid or gas volume, right? You just change the independent feature and train a different model. But if I'd had a different data set that had, for example, pump jack failures for whatever reason, so you have like pressure, motor speed, all of these other features, and then determine whether or not it failed, you can look at what indicators will predict whether or not, for example, your site will go down. And that would be a fun model to build and train. But you take what you can get and you work with what you have. So we split it into training and testing, and then we need to standardize all of these values. Basically, all this is doing is it is taking the values in the independent features and making it so that their mean is 0 and their standard deviation is 1. All it does is it makes it so the model is trained more effectively. Save this scalar for later because we will want it. And then I was just taking a look at that. So ANN time. ANN stands for Artificial Neural Network. That's what we're building. And these are all of the imports that are required to build this. So we're just going to walk through this very slow but very high level. Basically all this is doing is, because I want to run hyperparameter tuning on this later to find the most effective setup for the best predictions, you have to make some sort of function so you can call it later in this classifier. But all we did, made a small model, added one layer of neurons with an activation function of ReLU, and then for the input shape, obviously there's 7 features, so you need 7 inputs, so you can have one for each input feature. And then depending on the number of layers we have, add the number of neurons, same activation function. Obviously don't worry too much about what that is, but this part and this part are important. So because this is trying to predict a numerical value, we are interested in having it have as low as possible mean squared error, which basically is how far is my prediction off of my best fit line for my graph, is all that means. But if we were trying to say predict whether or not something was going to fail, and that would be more of a Boolean value, we could use sigmoid activation function with binary cross entropy. We could use the accuracy metric and then also get a confusion matrix going on to find out how many true positives and true negatives we have, and then obviously we try and minimize false positives. Or if we had multiple instances that we were interested in, we could use softmax and we could do categorical cross entropy. Right? So it's all a matter of what it is you're trying to predict and how you design it. It's not crazy complicated. The biggest thing to know is what activation function you want in your neurons, and then what it is you're trying to get at the end. So anyway, all that is to say that this model is a Keras classifier. Basically, we're going to use this to perform hyperparameter tuning on it, and then these are the parameters of interest that we're going to try and flip around and find the highest values. And that's what this grid search does. Right, so basically all this is going to do is it's going to take our model that we made up here. It's going to take our parameter grid, which we also made up here. It's going to use all of the available processors, that's what that means. And it's going to cross-validate it 3 times, and it's going to show us stuff. That's the verbose equal to 1. And so all it's going to do is it's going to check every possible option for these parameters to find me the best one. So obviously fitting 3 folds for each of 288 candidates, totaling 864 fits. It took 142 minutes. So about 2.5 hours, a little bit under. But I got it all to work, and we got the best output model. So as you can see, epochs equal to 50, layers equal to 1, neurons to 16, optimizers atom, optimizer learning rate for the atom is 0.01. Cool. So we got all that to work, and then this early stopping is just if this value isn't progressing, we can end the model training early, is all that does. So then I was interested in doing a little bit of seeing for what it is I had. So it's like, okay, cool, they're all objects, and then we needed to train the model, and so we had to change some of the typings. We needed to change the data type of the dependent feature to be float, so we could actually, train the model with it. That's what this function then does, is it trains the model off of the best models that we found over here. And then that's what this is our output is for. So this is the actual model that's going to do the actual predicting. And so this is the input data of just some random values that I threw together to see how it would do. And obviously we called the predict function with this data and got our output as 48 cubic meters in that day given these values. And then I just changed some data typings around so that I could find min and max values for each of these values for the ignition side of this project. And so now we'll go and take a look at that real fast. So this specific part of the project is supposed to simulate one specific site. So obviously you're not going to have just one folder with 7 tags in it, right? You're going to have a whole folder tree of like LSD, site number, and then potential other things inside the site. And so there would need to be a handful of models, but this is more or less to show that you can have it set up this way as an on-demand call, or later I'll show the constant checking option. So all this does, when you press this button, it's going to send out a refresh, and so every one of these values is set up to run a script that I stored in the scripting section and choose a value between the min and the max value that we got earlier from over here. All this will do is it'll send out a refresh to all of these values. All of these values will then run the script over here to grab anything between the upper and lower limit that I specified. The predict function, however, is a little more interesting. So the predict function is going to grab all of the paths off of all of these tags, right? Because all of these tags are also going to be simultaneously written to, right? So I want to get all the paths, store them in an array, write all the values of these given texts fields to their specified tags, and then read them back, and then pull the data into an ordered dictionary. So this ordered dictionary is very important because you need to pass it in the order that the model was trained off of the same features. And then this is just going to call the server with the data. So this is the data, and then the server call function was also over in here. And so that's the server that we will talk about in just a sec here, the Flask server. So if we look over here when we run it, see it'll generate new values. We run the predict. That will give us the actual prediction value based off of these inputs, and obviously it's, if you take the 16 out, it has a placeholder volume of liquid for whatever, and then you can just put that back in. And then if you want, we also have it to add to the database other part of this system. So if we go over here into the Flask server, so all this is going to do is, it looks complicated, but it's really not that bad. Basically, I want to load the model that we stored earlier, that we trained. I want to load the scalar because I'm going to need the scalar, and obviously you can have multiple scalars. If you have, say, a categorical value, like say 6 different values, you need to put those in terms of numbers. So you can, like one hot encoding, for example, is one option. You can store all of those models as pickle files and pull them into your server later. So then this is the features for this specific model. So basically I need to know that every header that I have is accepted by the system, by my model specifically, and it all needs to be there, right? And so if it's not there, it won't run the model. So that's what this is doing. So this data is just going to get the body of the request, and then this is going to check to see that every feature that exists up here is also in the actual JSON, and if not, obviously return 400 error. But if it is all there, we can transform that data, because it's an ordered Python dictionary, right? We can transform that data into a pandas data frame, pass that data frame into the scalar transformer, so it's all 0 scaled and has the mean 0 and standard deviation of 1 again, and then predict off of this model, which is off of this specific transformed data, return the data as a float, and then return the prediction. So that's what that is doing when we're pressing this predict button. It's doing all of those steps and returning that value. And also I had a good time with the the CSS for this project. And so that is this part of the server, right? So you can see it's in 35 milliseconds. It took that data, ran the prediction, and now it's sitting idle waiting for the next endpoint hit. And so if we go over here to the persistent one, the persistent check. This one was the more complicated side to do. So obviously you can see it's just the local host port 5000, the base stuff off of the Flask server with the endpoint predict, which is specified over here. Right. So all this is going to do is I want this to call my server with the data that I'm going to give lower down. So it's the same function as the one I showed in the Ignition server. This one's just a little bit newer because Ignition runs Python 2. So if you want to make external HTTP requests, you have to use, for example, the urlib2 Python library. It's older, so you have to pay attention to that. This is just newer. It works the exact same. So we'll come back to this run function in just a sec. But basically what this is going to do is every X minutes, so in other words every 1 minute at this point because I'm just showing you, I want you to call this function run, which is up here, and then every time that's done, run this pending. So every time you finish that request, take everything you've gathered and run it. Okay? So what this is going to do is it is going to create a MySQL database virtual connection, which I also have running on my local system, hence localhost, with the username and database, which are environment values, which I've specified elsewhere because obviously I don't need those in here. It's generally just more secure to put it this way, and also I don't have to show any of it. But this is timestamping. So this is the current time as of when the actual function will execute. This is minutes ago, which is however many minutes. I have it set up to 10 minutes ago right now. Usually you'd want the amount of time every time it's running to line up with the same amount of time in the back. So for example, every 10 minutes, go back 10 minutes, run the predictions. And so all this is going to do is pull everything from the oil table where the timestamp is greater than this minutes ago tuple. So you can't pass a string, you have to pass a tuple, whatever. So return all the records that you got off of that query, and then go into actually processing it. So print the current timestamp just so I can have an idea of where we are. And then for every row in my result, so basically every item in my list, because it's going to return a list, but you can just think of it like a data table. You need to make another ordered dictionary of all of the return types. So the first one's going to be the ID, the second one is going to be the timestamp, which is index 0 and index 1 respectively, and then index 2 is going to be the first one from the actual table here. So as you can see, ID, timestamp, then liquid volume, gas volume, water volume, right? And then result is equal to the call server of data, so we call the Ignition server with this function with this data, and then print the result. And then obviously every time this happens, we do it, we then close the database, because if you don't close it and then reopen it, you will be pulling the same data every single time. You have to refresh the connection, you're not going to get dynamic data. And so as you can see, it just finished its run. So 15 was the last one. If we come over here, prediction 39, add it to the database. 16, add it to the database. 26, add it to the database. And so now we can just wait for that to finish its thing. And when it does come around and start its execution again, it will hit all the ones that are 10 minutes behind, plus the ones that we've just added, right? So that's the joy of this. And so what you can do, for example, is you can take this result, instead of just printing it, you could print it just to have the server log, but you could also, for example, implement a Twilio texting service into your code. You could also put just an old school email STP server right? Oh, see? So it's grabbing all the old ones that already did, 13, 33, 15, and then it'll grab the new ones that we did, 39, see? 16, and there's 26, I believe, yep. So, and then once it hits that threshold, it won't pull that data anymore, and then we don't need it. But what you can do, you could send the text, you could send an email. Basically what this is going to do is it's going to monitor the database constantly, which if you have, for example, MySQL database, however it is you want to set it up, right? But every single one of those tags, right, presumably, you're going to want set up to some sort of database somewhere. And so every one of these tags that's going to have live PLC SCADA data, you can then save that data to a database and then run predictions off of that data as it's coming in, which is super cool. Which then gives another level to, you now have predictive data, and if something fails entirely, then you have the alarming system of Ignition, for example. Or if you wanted to look at reporting, some of this stuff would be very helpful for predictive reporting or things like that. So there's a lot of cool options in terms of in Ignition or outside of Ignition, but just relaying the two together, right? And obviously the on-demand one doesn't make quite as much sense because it's a nice idea to have a prediction of what's going to happen if you needed to just pull it off of Ignition for a specific site, fill in the information you're interested in, and run the model. But the predictive model that just runs constantly off of the database generally would be better for actual monitoring of a handful of different things. You could monitor well site down, you could monitor anomalies in your network detection, you can, for like cybersecurity, you can do all sorts of stuff, and that's why it's cool. But that concludes the prediction demo. So hopefully you all enjoyed this particular project that I was able to put together real fast and show you. And I hope you all have a good day, and bye-bye.